So today's lesson is going to be on the chain rule. After this, I will have pretty much taught you all you need to know about taking derivatives so we can combine lots of strategies together, which we'll also do at the end of this lesson. So first we're going to do a little review of composite functions. And so a composite function looks like this. We could have two functions, say f at x is the square root of x, and g of x is x plus 5. So then what would be f at g of 4? Okay, well, g at 4 would be 4 plus 5, which is 9. So then what you're trying to find then is f of 9. So sub 9 in here, square root of 9 is 3. But would that be the same as g of f at 4? Well, f at 4 is the square root of 4, which is 2. So that equals g at 2. And g at 2 is, well, 2 plus 5, that's 7. So no, I've already written down here, they do not equal. And you can prove that if you just use x instead of any specific value, even though we just did prove it with a specific value. So substituting g of x, which is x plus 5, into f at x, we get the square root of x plus 5. But substituting the square root of x into g of x, all we get is the square root of x and then plus 5. So they are definitely different. But our question is going to be, if we have some composite function, say we have h of x, which equals f at x, f of g of x, then what's the derivative of h of x? So that's what we're going to work with. And how we're going to figure that out is, I have sort of mentioned this before, and we have done problems like this before, but we're going to go a little bit deeper today, is h of x is going to be, first, we'll take this derivative, we'll find f prime of g at x, and then we will find g prime of x. We can write it in Leibniz notation as well, and when you write it in Leibniz notation, you can really see why it's called the chain rule. So dy by dx, you can have y as some function of u, and u of some function of x. So dy by dx will be dy by du multiplied by du by dx. So you can see the u's here are linked in almost like a chain, and you end up with dy by dx. So that's a lot of theory, but let me show you how this works practically. So here we have some function h. Okay, and it's written as x squared plus x to the power of 3 over 2. So that's a composite function. Right? You can think of it as g of x being x squared plus x, and you can think of f at x in this case being x to the 3 halves. So to find h prime of x, we are first going to, let's go back up here. We're going to first find f prime of g of x. So what we'll do is we'll think of this bracket as our g of x, which it is. So we're just going to leave it there. And we'll take that 3 halves, multiply it in front, almost as if we're just doing f at x. So we get that 3 halves, but it's g of x, so we got this, not 2, just x squared plus x, all to the power of 3 halves. So there's f prime of g of x. And then we have to multiply that by g prime of x. So we need to find the derivative of what's inside the bracket. Right? So x squared becomes 2x, and x just becomes 1. So there you go. There's h prime of x. So let's try this with Leibniz notation. In the next question, I'm going to change color. Here you have y equals u cubed minus 2u plus 1. And u is 2 root of x. So we need to find dy by dx and then solve for that at x equals 4. Okay. Well, if y equals u cubed minus 2u plus 1, dy by dx is going to be dy by du times by du by dx. Alright, so first take the derivative of y with respect to u. Alright, so u cubed is going to become 3u squared. Let's put all this in brackets. Minus 2u will become minus 2, and derivative of 1 is just 0. Now we have to multiply that by the derivative of u with respect to x. So that is 2 times the root of x, but you can think of it as 2 times x to the power of 1/2. So we have that 2 out in front. And then the 1/2 we're going to multiply by 1/2. And we'll get x, subtract 1 from the exponent. So 1/2 minus 1 is negative 1/2. Alright, so there's our answer, but we can just clean it up a bit. 2 times 1/2 just disappears. And we end up with 3u squared minus 2 over the square root of x. And then we could substitute u in. So u is 2 root x. So let me just continue over here because I'm running out of room. So we have 3. This is 2 root x all squared minus 2 over root x. Okay, you square that, you have 2 squared, which is 4, times 3, which is 12. Root x just becomes x, right? Root x squared. And then we have minus 2 all over root x. And then the question asks for what this equals at x equals 4. So if you substitute x equals 4 into it, you get 12 times 4 minus 2, which is 48 minus 2, 46, divided by the square root of 4, which is just 2. So 46 divided by 2 is 23. So this we have seen before, right? It's similar to what we've seen before. If you have a power of a function, right, like this one, you have a function x squared minus 5, and then you're taking that all to some power. And if you want to find the derivative of that function, let's say x squared minus 5 is g of x to the power of n, first you bring the n out in front, just like you're applying the power rule to that function g of x. So multiply it by the function g of x to the power of subtract 1 from the exponent, and then find the derivative of that function. So in this case, let me write this over here. We have y equals x squared minus 5. So that's our function, all to the power of 7. So dy by dx will equal, first apply the power rule to the function g of x, so 7 times that function x squared minus 5, subtract 1 from the exponent, and then multiply by the derivative of that function, which is x squared becomes 2x, and 5 becomes 0. So we're left with 14x times x squared minus 5 to the power of 6. Yeah, so for the first one, yeah, that should not have been 3 over 2. 1 over 2. Subtract 1 from the exponent. There we go. All fixed. All right, so let's try some sample questions. So our first one here says, well, using Desmos graph, so I did that for you, but then we're going to find the equation of the tangent at that point 2, 1 on the graph. So we have a point, right? You want to find the equation of a line. You need a point and the slope. So to find the slope, then we need to find the derivative of that function at the point x equals 2. So let's do that. But first I'm going to rewrite the function as 8 times by x squared plus 4 to the power of minus 1. So now I can apply the chain rule. So the derivative of that function then will be 8. So multiply by the exponent, -1, times by that function x squared plus 4, subtract 1 from the exponent, so 1 minus 1, -2, and then multiply that by the derivative of the function. So x squared becomes 2x, and 4 becomes 0. So we get minus 8 times 2, so minus 16x times x squared plus 4. So there's our derivative, right? Sorry, to the power of minus 2. And I can rewrite that over here a little bit more neatly without the negative exponent. So f prime of x equals negative 16x, all divided by x squared plus 4 to the power of 2. All right, and now I can find out what f prime of x is at 2. So we're just substituting 2, so minus 16 times 2 is minus 32, divided by 2 squared, so 4, plus 4, which is 8 squared, is 64, so that's minus 1/2. So now our equation of the line, we can use the slope equation, where m equals y minus y naught divided by x minus x naught. Right? M is -1/2. Y naught is our known y coordinate for a point, which is 1. So y minus 1. And x naught is our known x coordinate, which is 2. So x minus 2. Right? And you can rearrange that to either standard form or slope-intercept form, whatever you prefer. I'll put it here as slope-intercept form. So now that we have the chain rule there, let's go have some real fun with derivatives. So I'm done teaching you about derivatives. So we're going to start applying all sorts of different rules in one function. So let's look at example 2 here. So example 2 says differentiate the following functions, and we can leave our answer in factored form. We don't have to expand the whole thing. But notice what we have here. We have some function, g of x, to the power of 4. So we have a chain rule right there. But then we're multiplying, so we have a product rule too. Some other function to the power of 3, so another chain rule. That's going to be fun. So let's do this. So h prime of x. So first, product rule. We're going to find the derivative of this part. So we're going to apply the chain rule. So applying the chain rule, we're going to get a 4 in front, times that function x squared plus 3. Subtract 1 from the exponent, so 4 minus 1 is 3. And multiply the derivative of the function, which gives us 2x. And then multiply by the second portion, just the second portion, not its derivative. So that's going to be 4x minus 5 cubed. Now we're going to add. This time, we just leave the first part. So this is the product rule I'm applying here. Plus 3 to the power of 4. Multiply by the derivative of the second part. So we're going to have to apply the chain rule here. So bring the 3 out in front of the function. Multiply by the function, 4x minus 5. Subtract 1 from the exponent. So 3 minus 1 is 2. And then multiply the derivative of this function, which would be 4. So if everyone's okay then with how we applied chain rules within a product rule for that first step, from here on out, we're just going to clean things up. All right, because let's see, we have 4 times 2x, so we have 8x times x squared plus 3. all cubed times 4x minus 5 cubed. And then we're going to add, we have 4 times 3, which is 12. X squared plus 3 to the power of 4 times 4x minus 5 squared. Now what we can do is sort of pull out a common factor. So in our coefficients, I can pull out a 4. And then I have x squared plus 3 cubed and 1 to the 4. So I can at least pull out a cubed. And I have 4x minus 5. I have a square over here and a cubed here. So I said cubed, but I wrote squared. So I can at least pull out a 4x minus 5 squared. So all times by, okay, our coefficient is going to need to be 2x here. We have our x squared plus 3 cubed, but we need one more 4x minus 5. All right, so here our coefficient will need to be 3. And in this case, we have our 4x plus 5 squared, but we need one more x squared plus 3. Okay, not so bad. Do a little bit more cleaning up here. So we're going to expand these in the bracket. So we'll get 8x squared minus 10x plus 3x squared plus 9. And finally, just collect like terms in there. So we have 8x squared, oh, not 8x squared, 8 plus 3, so 11x squared minus 10x plus 9. And there we go. We're done. There's the derivative of h of x. All right, so for our next one, we have a chain rule. But you'll notice that the function in the chain rule is a quotient rule. So we're going to be applying both there. So to find g prime of x, first, let's apply the chain rule. So bring 10 out front, multiply by that function, 1 plus x squared, all over 1 minus x squared. Subtract 1 from the exponent, so 10 minus 1 is 9. And then, I might run out of space here, multiply by the derivative of this function in the bracket there. Well, that derivative is a quotient rule. So let's write what that's going to be. So first we're going to take the derivative of the numerator, which is 2x. Multiply that by the denominator, so 1 minus x squared. And then we're going to subtract the numerator, 1 plus x squared. Multiply that by the derivative of the denominator, which is minus 2x. And then divide by the denominator squared. So 1 minus x squared, all squared. So now we're just going to clean this up, and I'm just going to put the equal sign over here so I have a little more room there. So we have 10 times 1 plus x squared, all over 1 minus x squared to the power of 9. So let's clean up this large bracket here. So we'll expand the numerator, so we have 2x minus 2x cubed. And then we're going to have a negative 1 times negative 2x. So we're going to have plus 2x. And then negative x squared times negative 2x. So plus 2x cubed. All divided by, I'm just going to leave that as 1 minus x squared squared. All right, so here I have a negative 2x cubed and a plus 2x cubed. So they're going to cancel. And I'm left with 4x. So I can pull that out. So 4x times 10 is 40x. Okay, and then I've got this 1 plus x squared to the power of 9. And on the denominator, we have 1 minus x squared to the power of 9, multiplied by the same thing, 1 minus x squared to the power of 2, so we can add our exponents and write 1 minus x squared to the power of 11. There we go, we're done.